Hello, HSC 110, Medical Terminology and Body Systems. This is Dr. Teresa. In this video, we're going to go through Chapter 6, the Muscular System. This chapter in your book starts on page 166. So if you want to, you can follow along with me as you go through your textbook material, and I point out some of the things we want to focus on. The first thing we want to do is look at the different types of muscle tissue within the body. We have three types. There's skeletal muscle, cardiac muscle, and smooth muscle. And each one will be in different or varying places and have some unique and interesting properties. So skeletal muscle, this is the muscle that attaches to bone. This type of muscle tissue is largely responsible for you being able to move. It's also known as striated muscle. It's called this because histologically, and you can see on this picture, as well as pictures in your book, that it looks like it has stripes. We call these stripes striations, so it's also known as striated muscle. And we can call skeletal muscle voluntary muscle. It's called voluntary because it's stimulated by, usually, consciously directed by nerve activity. Like you can sit there and think, I want to move my toe, and then make your toe move, which when we're talking cardiac muscle as well as smooth muscle, you can't dictate its actions. It's off doing autonomic functions. An individual muscle cell we call a muscle fiber. This is going to be relevant as we go through the nomenclature, and also on your quiz number 2, where we have sections 4, 5, and 6, or chapters 4, 5, and 6. You're going to need to understand then how we name all of these parts, starting with the muscle fiber. And it's called that because it's long and it looks like a thread. Now, this muscle fiber has many nuclei, or what we would call multinucleated. So that's going to be relevant as we're learning about the different types of muscle tissue. That skeletal muscle is multinucleated and is striped or striated. Some fibers will run the length of a muscle and others will be a lot shorter, so their length will vary. Now, the number of muscle fibers that we are born with, there's a genetic determination or predisposition to that. So it's going to be different depending on multi-factors, and genetics plays a part. I think you guys have heard me say multiple times that genetics delivers contribution, not absolute condition, representation, or manifestation. So a skeletal muscle fiber can grow in length and diameter as we age. Adults can increase the fiber diameter and strength through resistance training or motions that will provide us some resistance. Skeletal muscle is highly organized. The cell membrane of a muscle fiber is called a sarcolemma. The sarcolemma of each fiber is covered with something called endomysium. This is a sheath of connective tissue. So we have a fiber which is a cell, going to be covered by something called the endomysium. Remember, the plasma membrane or the cell membrane of the fiber is called the sarcolemma. Let me just make you aware that anytime we see sarco, that should give us an indicator we're dealing with muscles. Groups of muscle fibers will be bundled together and they'll provide a fibrous membrane called a perimysium. These will be put in a unit known as a fascicle. So let's look at our picture here. Here we have our muscle fiber, the membrane again being the sarcolemma. There will be endomysium surrounding each fiber. And then we'll have groups of fibers bundled together to create the fascicle. The fascicle will be wrapped in perimysium. All of the fascicles in a muscle then will be enclosed by what we call epimysium. The epimysium is the wrapping paper around the entire fascicle or fascicles. Epimysium is thicker than the endomysium. The endomysium is a thinner covering. The epimysium will connect both ends of the muscle tissue with either a tendon. Remember, we learned that in the last chapter that tendons will connect a muscle to a bone. Or it will be connected in what's called an aponeurosis. So I'm going to say that again. The epimysium of a muscle, which is going to be the wrapping paper around the entire muscle, is going to be connected into either a tendon or an aponeurosis. The aponeurosis is another connective tissue. The tendons or the aponeurosis will directly connect a muscle to a bone or cartilage or other connective tissue. When we talk about smooth muscle does not have the striations. The cells are small, they're kind of spindle-like, so they're not the long threads that we would see in a skeletal muscle. These are muscles that are considered involuntary because we don't have that conscious control and they're autonomic. They kind of off doing their thing. They'll be regulated and stimulated by something other than us telling what to do. These cells will have a single nucleus in contrast to the skeletal muscle, which was multinucleated. Smooth muscle is also known as visceral muscle, and it's usually found in the walls of organs. This is found in the stomach, the bladder, your arteries. Smooth muscle cells tend to be arranged in layers, with one layer running lengthwise and the other surrounding the organ in which the muscles are contained. The coordinated alternate contracting and relaxing of these layers will change the size and the shape of the organ and can aid in the moving in the contents of the organ. So if we're thinking like about the stomach, right, or the intestines, the contraction of these muscles is what helps propel something through the vessel, and same with your arteries as well. Interestingly, with smooth muscle, they can do some sustained contractions for longer periods of time than a skeletal muscle can. When we get to cardiac muscle, this is muscle located within the walls of the heart. This is the only place cardiac muscle is found. Cardiac muscle cells are really neat little things. They're branched. They are striated or striped. They're definitely involuntary. And they're under the control also of the autonomic nervous system, meaning not conscious control. Okay, autonomic nervous system divisions, which we will learn when we get there, but just for your awareness of what that means, is the divisions of the autonomic nervous system that are in charge of this as well as the smooth muscle are the sympathetic and parasympathetic nervous systems. If you've never heard of them before, that's what they are. And again, we will get into them later and we'll see them popping up a lot. Cardiac cells will be arranged in a network of figure eights or spiral shaped bundles that will join together at junctions called intercalated discs. So one of the identifying markers of cardiac muscle is its branching pattern within the cardiac muscle cells, but also these darker lines. If you're looking at this slide or the slides on page 168, same picture, these darker margins of the cells are junctions, gap junctions between cells that will join them, but these guys are called intercalated discs. A gap junction allows for fluid and ions to be passed in between cells so that a particular tissue can sort of function as one entire unit. And that is the case here with the heart muscle. You have a little graph or chart I'm going to reference here that I think is worthy of looking at. Your textbook has some amazing charts that I encourage you to use. It's on page 169 in your textbook, and it goes through the 3 different types of muscle and compares them as far as the cell structure, meaning, their shape and the number of nuclei. Also the control, whether it's voluntary or involuntary, and then places that will find them. So that's a nice little chart for reference that I would definitely take a look at. When we're looking at muscles, okay, I think we understand muscles a little bit just because, they're part of our bodies. So hopefully we have an awareness of how they work, but we're going to get into really the truth of some of the properties of muscle tissue and what makes it muscle tissue. It has to have 4 characteristics present. It has to be or express irritability, extensibility, elasticity, and contractility. So it has to be able to respond to a stimuli. That's the irritability part. It has to be able to stretch and change its shape, and then also shorten and contract. Extensibility, the ability to be stretched, and elasticity, which is the ability to return to normal, are going to be really relevant as we look at how these guys are able to function better. Contractility in contrast to extensibility. So let me clarify that. Extensibility, it can become longer, elasticity back to normal or neutral, and contractility is the shortening. When we look at skeletal muscle specifically and how it goes through a contraction, contraction again tells us it's a shortening of the muscle. And it usually means like there's tension in the muscle. It's doing work when it's contracted. It's not at rest. But a muscle doesn't always shorten when there's tension in the muscle. When a skeletal muscle develops tension, one of three actions can occur. The muscle can shorten, it can remain the same length, or it can get long. For example, when the biceps muscle develops tension and shortens, your hand can move up to your shoulder. This is called a concentric contraction. The bicep is performing the role of what we call the agonist or the prime mover in this situation. The opposing muscle group would be our triceps muscle, playing the role of the antagonist. So it's doing the opposite and opposing function. The antagonist may be completely at rest or relaxed, or it may hold a little bit of tension, depending on what type of movement style we're trying to do. A muscle can also lengthen while developing tension. So an example, if someone were to place in your hands a weight that was too heavy for you to hold, your bicep would develop tension. But if the weight's too heavy, you'd lower the weight and your bicep would lengthen. This type of action is what we call an eccentric contraction or a lengthening contraction. So there's still like this tension principle, okay? But it can be elongated. So what the word contraction, when we say it's a shortening, isn't really a full definition, is what we're trying to say. The concentric contraction would be the true shortening contraction or shortening due to the tension, whereas the eccentric contraction is tension that can be had or placed or held within a muscle while the muscle is actually lengthening. In a third scenario, you flex the muscle in your arm and you develop tension in both the biceps and triceps. This is called isometric contraction when there's no movement, but there's tension in both. So in isometrics, iso holds the same, metric measurement. There's no change in length. It's just a sustained contraction. You're going to have, when we go through any movement, also there are going to be variations and combinations of all of these. When we're talking about muscles and energy requirements, we have to understand that there's going to be a heat production. We know that when we exercise, there's generally an increase in body temperature, sometimes sweating. When we work a muscle, it generates heat. When you're not exercising the muscle, it's comprising approximately 40% of body mass and to generate the heat, and this helps maintain your normal body temperature just through regular metabolic processes. This is done by the requirement to form ATP. I'm certain we've all heard of ATP somewhere along the line, adenosine triphosphate. This is one of our very important molecules within our body that we like to have produced as an energy supplier due to the fact that it's easy to harvest the energy in the bond of one of the phosphate groups. It's easy to change it, relatively speaking, in contrast to other molecules. When we talk about a little bit more about the physiology of the muscle fibers, when we're looking at it from a really deep perspective, this gets really cool on how it all works. So I hope you find some magic in this section. So as we're learning how a muscle actually gets to do the contraction, we do have to go and understand the physiology of the cell. What you're going to learn, hopefully, about the human body, and I may have mentioned this previously, is that anytime you want to figure out why something is off, you really have to go into cellular mechanics, which, once you learn how the cell works and operates, and the membranes and receptors and ions go into that, that part that seems really tedious and that most people don't like, that broad-based chemistry part of things. Really, that's why things either go right or go wrong. So understanding that is paramount as we discuss health of the human body, and then correspondent quality of life from there. So when we're talking about muscle tissue, we have to discuss the motor unit. The muscle tissue can't contract or develop its tension unless it's stimulated by a nerve. This is the skeletal muscle contribution, or skeletal muscle physiology. We often call this arrangement the neuromuscular system. It's really discussing how neurology intertwines with the muscle. A nerve that stimulates a skeletal muscle under voluntary control, because it's skeletal, this would be known as the motor unit. A single motor neuron and all of the muscles that it stimulates is known as a motor unit. One motor neuron supplying impulses to a muscle can connect itself to that muscle anywhere from like 100 to 2,000 times, depending on the muscle and what it's intended to do. When we have smaller muscles, they're going to be responsible for finer motions, and that would be like something with our hands, perhaps. When we have larger muscles, they're going to have larger motor units, meaning larger amount of connection points, and that might be like our quadricep muscle. So in this picture, we get to see how these neuromuscular junctions or neuromuscular units look anatomically. On this picture, okay, to the left, that's a cross section or transverse section of your spinal cord. We can see that we have the cell body of neurons kind of anchored into the spinal cord. And then it will have these are axons, which we'll learn about when we get to the nervous system section more intimately. We'll leave the cell body and leave the spinal cord. Have these little tails then that will connect to muscle fibers in many different ways, many different areas, many different arrangements. When we have this nerve cell or neuron attached to the muscle fiber, it does so at a place where we would call the neuromuscular junction or the NMJ. On that, let's see if we can back this picture up and look at this again. So where this NMJ is located, we can see the very ends of this fiber from the neuron or the axon. It looks like little feet kind of that stick to the muscle fiber. These are called axon terminals. And they're relevant because a lot happens at this terminal end of the axon where it joins to whatever it wants to join to. In this case, it would be skeletal muscle fiber. Let's go over the parts of the NMJ. This bulb-looking thing would be the terminal axon. Or the end of the axon, the end of that nerve cell. Where it joins the muscle fiber, there will be a space. This is called the synaptic cleft. Within the axon terminal, we notice on this picture we have looks like little bubbles inside of it. There's something called a vesicle produced by a cell. It's going to have something in it. It's going to be moved somewhere. That cell needs to do some form of bulk transport with these things that it makes. In this case, it's made a neurotransmitter called acetylcholine. What will happen then is the chemicals within here, this neurotransmitter, will be pushed to the end of the axon terminal and released into the cleft. The muscle fiber then will have receptor sites within it to be able to pick up that acetylcholine. And that acetylcholine will then be responsible for the inspiration of the muscle contraction. Acetylcholine will make the sarcolemma, or the plasma membrane of the muscle fiber, temporarily permeable. It'll open channels that will allow sodium ions to invade the fiber and at the same time have potassium ions rush out. So we have the sodium potassium pump sort of doing its thing, kind of. Because more sodium enters than potassium leaves, the net effect is the creation of a relatively positive charge inside the muscle fiber or the muscle cell. This change in charge is known as depolarization. Depolarization is what will trigger the opening of additional channels in the membrane that will allow only the additional entry of sodium. This will flood positive ions into the fiber. And when this happens, it's like the reinstating of the charge difference from side to side of that membrane. This is what we call an action potential. We're going to see this in multiple scenarios, multiple cases. So learning how depolarization or repolarization works will be highly beneficial. So let me walk through those terms just a little bit. So anytime we see polarization, we understand that we have opposing forces, charges, or experiences, okay, across, in this case, across the cell membrane. Now you can apply this to anything, right? Dark and light are polar opposites. They're polarized from one another. Masculine and feminine, positive, negative. Anything that's polar, or like the North Pole, South Pole, opposing poles, opposition. When we have something in polarity, it will hold its opposition. So in the case of this across the cell membrane, we have polarity. We have a more positive charge on one side of the membrane than we do on the other. Anytime we have that, we have an action potential, meaning it is set up to be able to do an energy release. If we have an energy release, we have the ability to do work. As this situation of charge difference across a membrane begins to change, it depolarizes, meaning it's going to bring it more to a neutral charge on either side of that membrane. Same amount of positive ions over here, match the same amount of positive ions over here. When we have something that's been depolarized, again, that is a shift in or release in energy by a system, and therefore it gets to do work. When we talk about the sarcomere now, we have to again go into these cells, look how they're comprised, look at their arrangement, so we understand this a little bit better. In this picture, or in the picture on page 174 in your book, you're seeing what creates the striations in a skeletal muscle. It is due to the arrangement of protein filaments of varying sizes. These filaments are primarily actin and myosin. You may have heard of that, and we're going to learn a little bit about it. So when we're talking how this system not only delivers the appearance of the striations, but also the ability for the entire contraction process to take place. This is what we're stepping into. So glucose is stored in the form of glycogen within a muscle cell that will provide energy for creating that action potential. So if we want to keep the charge difference from side to side, that's going to require energy. That's what this is saying. So skeletal muscle will require a pretty easy, accessible source for utilization to reinstate this action potential. There's something called phosphocreatine within the cell that enables the transfer of energy to these protein filaments, actin and myosin. The actin and myosin reside in this arrangement called a sarcomere. Again, this is the functional unit of the muscle contraction or the muscle tissue. The myosin filaments, these are in this picture, these red strands of protein, and it looks like they have little spikes sticking off of them. These are what are called the heads on a myosin filament. When the sarcomere is activated by an action potential, again, that's all starting from that neuromuscular junction, releasing acetylcholine into the synaptic cleft. The sarcoplasm picks up or receives the acetylcholine, and it's going to start working on this system by way of the action potential that's been inspired. So what happens here then is once the sarcomere, this unit of arrangement, gets activated by the action potential, these heads that are sticking off of that red myosin filament form what's called a cross bridge. The cross bridge will contract. It will pull the actin filaments toward the center of the sarcomere. The cross bridge, where it connects, will attach, pull, and release multiple times. Then the calcium ions released with the arrival of the action potential will enable the myosin head to attach to the actin filament. So this process gets a little bit more detailed for our purposes. Just the awareness of the fact that the heads of the myosin, again, those little things that are sticking out of the red threads on this picture, they will link to the action and they'll kind of slide across each other. Okay, that is what delivers the quote unquote contraction of the muscle, okay, or the muscle fibers. The neuromuscular system can produce slow, gentle movements, but also fast ones. There are only a small number of action potentials that will be required for something slow. Now, if we have a bigger muscle requiring, bigger movement, we're going to require more action potentials to be in play. When a muscle receives an action potential, the muscle unit always develops its maximum tension. This is known as the all or none law. Either it's doing it or it's not. It's not gonna do a partial piece of it. But because each whole muscle includes multiple motor units, there can be simultaneous activation of these motor units that are required to help the muscle reach maximum tension. We can talk here about something. Well, let me look at this. Let's look at this graph first. Okay, this is maximum tension and return to relaxation. If you look at the time span here, also the amount of tension delivered in a muscle, you can have a stimulus, but if it's not enough to reach a threshold, it's not gonna have the muscle go into contraction. That is basically what we're saying there. There is something called tetanus within a muscle. This is with high frequency stimulation, the muscle will develop a sustained maximal level of tension called tetanus. And this is what the tetanus shot is trying to stop. You don't want all your muscles in a state of tetany. When we talk about muscle fibers, there are different types. There are slow twitch type 1 fibers and then fast twitch. So the slow twitch fibers well, let's go into fast twitch a little bit. Okay, within the fast twitch fibers, we have they're type 2, but we have an A and B. The contraction speed of the type 2 fibers will fall somewhere between slow twitch fibers and type 2B fibers, which are what we would call classic fast twitch. So the type 2A, they're kind of like this in-between phase. Now, when we say slow twitch, it's because they're slower moving muscle, slower contracting muscle. So they're going to be different muscles activated for different purposes. The type 2B fibers, they contract rapidly, but then they also fatigue rapidly because they're utilizing resources. So within muscle physiology, you have to understand that if you can't reinstate the action potential, the muscle can't fire again. So the whole system has to be able to be reset. There has to be a large enough stimulus to be able to even start or inspire this action. So when we're talking the difference in fiber per what activity we would see them in, fast twitch fibers we might see in people that sprint or jump or similar activities. Whereas the slow twitch, this is something that will require endurance, like distance running or swimming, due to the slow twitch effect. So you could now, when we are talking availability of these fibers, there is a genetic predisposition or contributing factor to the type of fiber that a person will have or have available to them, which is why perhaps in certain athletic events we see a difference, right? In performance, maybe we have a swimmer that we know does really great. One contributing factor, not the only thing, will be for that person to have a certain availability of a particular fiber type, which can then predispose us to an activity we're better at. Just a personal share for myself, I don't do anything fast. So as far as exercising, I definitely have a better ability to do endurance anything. So that would tell me that on board, probably just inherently, I have more slow twitch fibers. Now, what we also notice, though, even in regards to the genetic predisposition, we can change the fiber type within an individual. So we do at this point understand that fast twitch fibers can be converted to a slow twitch with the right type of training. And we can convert maybe between fast twitch types. When we're talking muscles, then we have to understand that there can be different fiber arrangements. For example, we could have a fusiform form muscle or a bundled form muscle or a triangular form muscle. So fusiform, this is the biceps brachii. An example of a bundled muscle would be the rectus abdominis. And then the triangular shape would be the pectoralis major. In a parallel fibered architecture, we're going to see most of the fibers run parallel to one another. And this is what we're seeing. These examples that I've mentioned, fusiform, bundled, and triangular, are examples of the parallel fiber architecture. This arrangement of fibers will enable shortening of the muscle and the movement of a body segment through a larger range of motion. Within a pennate fiber architecture, we can see three examples: the unipennate, the bipennate, and the pennant. So example, the unipennant would be the muscles in your hand. The bipennant muscle would be a rectus femoris, and then a multipennant muscle would be the example of a deltoid muscle. In this type of architecture, the fibers will attach obliquely to a central tendon, and then in some cases to more than one. The unipennant has an arrangement where the fibers are aligned in one direction. The bipennant would have the attachment to that central tendon in the center, and then the multipennant. These are where fibers that attach to the central tendon will be in more than two directions. Couple things that you can look over this in your book. I'm going to ask you to do that on page 176 when we're looking at adaptations of the NMJ. Again, that NMJ is a big deal, neuromuscular junction, where the axon of the neurons come and join with the muscle fibers. In this little section on this page in the tan box, we get to learn a little bit more, read on about the neuromuscular junction in regards to fast and slow twitch fibers and how they're different. We get to see how the NMJ adapts with aging and how this remodels over time. And then how exercise can change these junctions as well. And I think that's relevant as we're kind of learning through this. Okay, as we're looking at the strength of a muscle, we have to understand a few concepts, like what delivers one muscle beyond size to be considered like really strong, or its ability or capacity to do a particular job. So we have to understand the words strength and then power, and we'll go into each category and just talk through a little bit of it. We also have to understand that their muscle fatigue comes into play, and I mentioned that already, kind of indirectly. So we might want to think that strength is the force that a muscle gets to produce. It is impossible, however, to measure muscle force directly without penetrating the body, which anytime we do that, that's invasive. We have to understand too that when we're talking skeletal muscle specifically, its job is to move us or move bones, move a lever system. So if we're moving things, we have joints, and there are going to be multiple muscles that cross a joint. We have to understand that many exercises will involve more than one joint or one particular movement. So when we're assessing strength, a good way to measure this is the amount of torque or rotary force that a muscle can generate. Torque is the product of the size of a force and the perpendicular distance of that force from an axis of rotation. The torque produced by a muscle is the product of the muscle force and the perpendicular distance from the muscle attachment to the center of rotation of the joint. The more torque that a muscle generates, the greater the tendency for movement. We can look at torque with a tool called a dynamometer to get an idea of this. When we look at power, different than strength, mechanical power is force multiplied by velocity. Muscular power then is muscle force multiplied by muscle shortening velocity during contraction. Like the strength of the muscle and how we measure that, power is typically generated by several different muscles working collectively. So sprinting might be a good example of a way to quantify power. When we talk about endurance, the ability of a muscle to produce tension over a period of time. We mentioned that with slow twitch fibers. It's going to be different per activity, and muscle fatigue will be relevant in determining how long a muscle can withstand. And fatigue really comes from multiple factors like glucose available or tools, some kind of fuel available for energy production, plus being able to rid a muscle of metabolites. Muscle fatigue can be thought of as the opposite of muscular endurance. The faster a muscle fatigues, the less endurance it has. A variety of factors will affect this, like I mentioned. It can be the fiber composition, but also the temperature, the humidity of the environment. A muscle will reach absolute fatigue once it's unable to develop tension when it's being stimulated by a nerve. Okay, again, why would that happen? It can get stimulated, but if it doesn't have the energetic support to do all the internal physiology and the fibers, it can't happen.